Hello and welcome back. So now what we want to try to do is explain how a planet like Jupiter can actually change its orbit. And in order to explain this, you have to understand the concept of gravity, which always pulls. Okay, then understand the concept of energy, in particular kinetic energy. So kinetic energy is going to be 1/2 mv squared. So it's going to depend on the speed of the object. So the more speed an object has, the more kinetic energy it's going to have. Another concept that you need to understand is conservation of energy, so that you can't create or destroy energy. So if energy is being lost by something, then energy must be gained by something else. Okay, and then another concept that you're going to need to understand is centripetal force, which we talked about in a previous lesson, but I have a centripetal force demonstrator here, which I want to show you here in just a few moments. So last time we talked about Jupiter, and we said that Jupiter forms outside the ice line, but it's a little bit closer than what it is today. Then the next thing is that Jupiter's gravity is going to pull on the inner part of the disk. So let's draw a picture of what's going on here. That you're going to have the sun in the middle. Okay, then surrounding the sun is going to be a disk of material that is eventually going to become the terrestrial planets. Okay, then outside this disk of material, we're going to have Jupiter. And then outside of this is going to be another disk of material, which is going to be the outer part of the solar system. So that you got this inner disk right here, and then you've got this outer disk out here. And then in between the two disks is going to be where Jupiter is at. So Jupiter's gravity is going to be pulling on this part of the disk. And because gravity pulls, it's going to slow down the rotational rate of this inner disk. So if this thing slows down, then this means that the kinetic energy of this disk is going to start to decrease, because kinetic energy is 1/2 mv squared. So it depends on the speed. The faster something's moving, the more kinetic energy it's going to have. So because of the gravity of Jupiter, this disk is going to start to slow down in its rotation rate. Well, by conservation of energy, that means that something must speed up. And so that's going to be Jupiter. So the disk is going to slow down in its rotation rate, and Jupiter is going to speed up in its rotation rate. That's going to affect its orbit through centripetal force. So centripetal force is going to be equal to the mass of the object that's going around in a circle times the speed of the object going around in a circle squared, divided by the radius. So the radius would be the distance from the sun to Jupiter. Okay, so those are the letters that are in that formula there. So what I've got is a centripetal force demonstrator, which is always entertaining because I normally end up hitting myself in the head with it. So what this consists of is a plastic tube, and then there's a string that runs through it, and it's attached to a rubber stopper, and then the other end of the string is attached to some washers. So now the washers are going to represent the gravity of the sun. So notice what the gravity of the sun would do to Jupiter. So Jupiter is going to be the rubber stopper. And so if Jupiter was not moving, you can see, well, hopefully, there we go. You can see that Jupiter was pulled towards the sun. Okay, now what would happen though if I give Jupiter some rotational motion? So it's in orbit around the sun. So what I'm going to do here is I'm going to get down low. I'm going to get my face out of the way so I don't get hit in the head with this thing. Okay, did you notice that as this thing was going around and around, the radius, it changed? And did you notice that the faster it went around and around, the radius got larger? So hopefully you can see that from the formula. So let's take a look at the formula here. That the centripetal force is equal to the mass of the object going around, so that would be the mass of Jupiter, and then the speed of Jupiter squared, and then divided by r. Now, the force that is causing it is the gravity of the sun. So that would be the F in the formula. And so the mass of the gravity of the sun is not going to be changing that much. So F is going to be pretty much constant. And we said that the velocity was getting bigger. So if the velocity here, so let's make this very big. So let's say that the velocity got very, very large. How could we balance the equation? So let's say that this gets 2 times bigger in the V. What would we need to do to the bottom part in order to keep it in balance? Well, remember, it's 2 squared, so 2 times 2 is 4. So what we would need to do is we would need to change the radius by a factor of 4. The radius would have to get larger by a factor of 4 in order to balance the velocity if the velocity was to double. So the whole point is that the gravity of Jupiter is pulling on this disk. It's slowing the rotation rate of the disk, but in order to conserve energy, that means that Jupiter needs to pick up speed. As it picks up speed, its radius increases. And so that would mean that Jupiter would start to move further out in its orbit if that was the only thing that was happening. But remember that you also have this disk out here. So that disk out there is also pulling on Jupiter. So the outer disk pulls on Jupiter and it slows it down in the same way that Jupiter's gravity slowed down the rotation of this disk. And so if the Jupiter slows down, then according to this, its radius would get smaller. So we've got 2 competing forces acting on Jupiter. Its gravity on this disk makes it want to go further out in the solar system, and then the gravity of the outer disk on Jupiter makes it want to move further in. Well, there's more material in the outer part of the disk because it's bigger. So that means that the outer disk is winning, and Jupiter is going to start to move closer to the sun. Okay, now the next thing that's going to happen is the gravity of Jupiter is going to start to pull on this disk, and can you see how it's causing more of the disk material to be pulled over to the side where Jupiter is at? Now that material is eventually going to become the terrestrial planets. Well, if we didn't have this outer disk here, Jupiter would just continue to get closer and closer to the sun. And so we have actually observed this. There are objects the size of Jupiter, composed of gas, and they're very, very close to their parent stars. There's even one of these Jupiter-like planets is actually touching the outer atmosphere of its star. So some of these Jupiter planets can get very close to the sun. But that didn't happen to our Jupiter. Our Jupiter started to move close to the sun, but then it started to move further back into the solar system. And it was rescued by Saturn. So Saturn is further out here, and it is eating away at this outer disk. So Saturn is eating this outer disk, and then without the outer disk, then Jupiter can speed up, and Jupiter can start to move further out in the solar system. So Jupiter started to move towards the sun, but then it started to pull back out. Now, it's not due to anti-gravity, so don't get the idea. Gravity always pulls inwards. So it's a consequence of the speed of Jupiter, and centripetal force is causing it to do that. And then the leftover material in the disk then forms the inner planets. Okay, so we're going to take a break, and when we come back, we're going to talk about our lesson quiz.